Hi everyone, in today's lesson we're going to talk about continuity. So let's define it first. A function is continuous at any given point if and only if the limit from the left equals the limit from the right as well as the value of the function. So this part, the limit from the left equaling the limit from the right, that is just a regular limit as x approaches c. So the limit as a whole has to exist, and the limit as a whole has to equal the value of that function at that point. So what that means visually is a graph that you don't have to pick up your pencil for. So let's just say a parabola, for example. I can trace over this parabola without picking up my pencil. I could trace over maybe a polynomial function. This is like an x to the third function, right? Trace over, trace over, trace over. I don't have to pick up my pencil. So that's what this textbook definition of continuity means, is that all of these points will never have to be picked up if I traced over it. So let's talk about the types of discontinuities that we'll have. So a discontinuity is when there's a break in the continuity. So the first type is a removable discontinuity or a hole. So if you were to test for continuity, you're going to trace the curve, and whenever you have to pick up your pencil to jump over a hole and continue, that obviously means it's discontinuous because I had to lift up my pencil. So even here, trace, 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 pick up, and continue the trace. So therefore, that's a discontinuity. It's not fluid, it's not continuous. An infinite discontinuity is where we'll have a vertical asymptote. So an example could be if I'm approaching infinity and I pick up my pencil to go this way, I've picked up to go over this asymptote. Same thing here. I'll trace, jump over the asymptote, trace again. So I had to pick up my pencil, therefore it's discontinuous. Then we could also have a jump discontinuity. So I trace, 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 jump up, and I continue. This is more like a piecewise function. That would be a discontinuous function. An endpoint discontinuity is at the end, the function just ends. And a mixed discontinuity is where maybe there's a hole on the vertical asymptote. This one's not as common, but these are all the types of discontinuities that you have. So sometimes they'll ask you to name the type of discontinuity that you see. So the first one should actually be at x equals 2. And the second one should also be at x equals 2. So take a couple minutes and try to find the type of discontinuity and hit resume when you're ready for the answer. Okay, so the first one is called a removable discontinuity. Or in other words, a hole, right? If I'm trace, 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 there's a hole here, and I continue my trace. This here is the function value, and that has no bearing on whether it's continuous or not. The second one, you should have gotten that I had to trace, 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 pick up, and go along. So this is a jump discontinuity. The third one was an infinite discontinuity. And the last one was an endpoint discontinuity. All right, now the last thing I could ask you to do is redefine a function that's not continuous. So given this function f of x, I want you to find the value of k that will make this function continuous. So you should recognize that this is a piecewise function. So a piecewise function, we could have three scenarios. So we could have that it has a hole and then another hole, jump, right? Or it could have a hole that replaces and it looks like such. This is what we want. We want to make sure that there's a smooth connection, so that way we have a continuous function. So it's not like this where we have to trace, pick up, and keep going. This is discontinuous. So we want it to look something like this. So how do we do that? We have to use the limit of continuity. So in the beginning, we said the limit of continuity, or the definition of continuity, is the limit as x approaches some value, c, the limit as x approaches that value from the left, must equal the limit as x approaches c from the right, which must equal the value of that function. So what we're going to do is we're going to separate this piecewise function into two pieces. So as x is less than 3, we know that this is the left side of the graph. And as x is greater than or equal to 3, this is the right side of the graph. So if I want to find the limit as x approaches c from the left, or as x approaches 3 from the left, we're going to plug into the top function. And if I want to find from the right, we're going to plug into the bottom function. So first, let's change our c's to 3's. So we want to find the limit as x approaches 3 from the left, and I want to see that that's equal to the limit as x approaches 3 from the right, which must equal f of 3. So for the left side, we're going to plug in 3 into the top function. So 3 squared minus 1. That's 9 minus 1, which gives me 8. And then for the right side, I've got 2 times k, and x is 3, so that's 6k. And then f of 3 is the value of that function. So this one, we have to look at the closed circle. So my closed circle would be the one that has the line under it. So this one, right? So this would be the same as plugging in here, which is the right side. So 2k and x is 3. So 6k similarly. So just to solve, you're going to set any two of these equal to each other. So since these two are equal, we're going to set these two equal and solve. So 8 equals 6k, divide by 6, and we could reduce this to 4 over 3. So if I ask you to redefine the function, the answer is f of x equals x squared minus 1 when x is less than 3, and 2kx, so 2 times 4/3, which is our k, x, when x is greater than or equal to 3. So this is our redefined function. Now technically you should really simplify this to 8/3, but that would be your final redefined answer. So the last one is a little different because we have this rational function. So we're going to do things a little different. So the first thing that we're going to do is check for any holes or vertical asymptotes. And the way that we do that is we factor the top, the x squared minus x minus 6, and we factor the x minus 3. So by doing that, we'll get x minus 3, x plus 2, and on the bottom, we'll be left with x minus 3. So since these cancel, the hole is at x equals positive 3. It's always the opposite sign because really it's like you're taking the root of this, that's the hole. So if you were to do a t-chart, x minus 3 equals 0, that is your hole. So x is equal to 3. If there was any other parentheses on the bottom, that would be my vertical asymptote. So the thing that crosses off is the hole. Anything that's left over on the bottom, which nothing in this case, would be vertical asymptotes. So because this tells me there's a hole at 3, that makes sense here. We're going to use this function at the hole at x equals 3, and we're going to use this function everywhere else. So what we're going to do, since we simplified it, it simplifies to x plus 2. We're going to use that x plus 2, so f of x equals x plus 2 for when x is not equal to 3, and we're going to use k for when x is equal to 3. So if we want to find the value for k, all we have to do is find the y value of the hole. So step 2, find y value of hole. So to do that, you're going to plug x equals 3 into simplified equation. So my simplified equation is this x plus 2. So we're going to plug 3 in. So 3 plus 2, which gives me 5. So that is what k is. So if you redefine this, your k right here is going to be 5. So f of x equals x squared minus x minus 6 over x minus 3. When x does not equal 3, you want to use the original. And k is 5, so we're going to leave 5 there for when x is 3. So this is my redefined function. So this one in the middle was kind of like a preliminary step. You won't use that. It'll just be this. So don't stress if this was a little tricky. We're going to go over this more in class tomorrow. So if you have any questions, now is a good time to jot them down and then ask me in class tomorrow. All right, have a good night.